Good morning, Dr. Sir. Good morning, beta. Good morning. Good morning, Dr. Tokonami.
Yeah, good morning.
Abhishek, you can start and.
Okay, sir.
Okay. Okay.
Good morning, everyone. I welcome Professor Shinji Tokonami, sir, Professor Rohit Mehra, sir, and all the participants to day 2 of this GIAN course. Today's session will remark the beginning of insightful journey on measurement of techniques of radon isotopes, which will not only expand our theoretical understanding, but will also enhance the practical applications in the realm of environmental radioactivity. So without making more delay, I invite Professor Shinji Tokonami, sir, to start his talk of this day 2 of GIAN course.
Okay. Thank you very much. Hello, everyone. Yesterday, we stopped the talk with this slide on measurement of individual radon progeny concentrations. Before going to the next slide, I'd like to review two questions I got yesterday. First one, radon entry into buildings. There are two basic mechanisms, namely diffusion due to the gradient of radon concentration in the environment, advection caused by the pressure difference between building envelope and outdoor atmosphere. I received a question on radon entry rate. I'd like to introduce some information related to radon entry rate. According to ANSCARE 2000 report, radon entry rate expressed in becquerel per cubic meter hour is, let me see. This physical parameter is dominated by the following parameters. First one, surface area of the walls. Second, radon flux density. It is also influenced by radium-226 concentration and emanation coefficient, density of the material, porosity of dry earth material, and diffusion length in the material, and also the volume of the house. Also, I'd like to introduce the radon entry rate expressed in becquerel per second based on the theoretical approach. Here are dominant parameters for radon entry rate. The first, radon concentration in solid gas under the house at infinite depths. Second, airflow entering the room due to existing pressure difference, which includes gravitational acceleration, height of building, difference in air density determined by the temperature difference between indoors and outdoors, and leakage area, and etc. It is not easy to define the radon entry rate, which includes a lot of physical parameters like this. The second question was on an attached fraction. According to ICRP publication 137, the unattached fraction depends inversely on the ambient particle concentration. The mean values measured in dwellings range between 0.04 and 0.2. Furthermore, measurement of the unattached fraction in indoor workplaces such as schools and offices show a wide range of values, typically between 0.03 and 0.15. So I would say the typical unattached fraction value is it is 0.08 for indoor workplaces, 0.01 for mines, and 0.15 for tourist cave. So So we are going to today's lecture regarding measurement of individual radon concentrations. There are many types of progeny measurement techniques. The first one I would like to introduce is Thibault method. This method was created in 1953. It is one of the earliest measurement methods. The method records the total alpha counting rate at 5, 15, and 30 minutes after the end of the 5-minute sampling, and the 3 radon progeny concentrations are calculated by resolved calculation. Due to its simplicity, it was widely used in the mines. The Thomas method. It was created in 1972. Replacing counting rate at certain time with total counts in different interval. This method records the total alpha counts in 2 to 5, 6 to 20, and 21 to 30 minutes after 5 minutes sampling. In order to obtain higher sensitivity, we have to get a higher flow rate, geometric efficiency, and longer measurement period. Least square method. It was developed by Ravi and Ren in 1969. This method records the total counts from the sample during various periods of time and uses the least square fit for calculation. Numerical solution gives precise results through computer program. Decay method with alpha spectroscopy. This technique is called Maltz method, developed in 1969. This method consists of a proper filter, a silicon semiconductor detector, and MCA. Separate determination of polonium-218 and polonium-214 activities are made by counting at 2 different times, namely 5 minutes and 30 minutes after sampling. This is for measurement of working level. Kuznets method was proposed by Kuznets in 1956. In this method, air is sampled through a filter paper for a short time, commonly 5 or 10 minutes. At least 40 minutes is allowed to elapse after sampling is completed before the count rate from the deposit alpha activity on the filter paper is measured. This method only provides an estimate of working levels and gives no information on the individual progeny concentrations. This method was later modified. I'd like to show you the commercial product of working level monitor, namely Pylon WLX. Features a state-of-the-art solid-state detector and employs sophisticated algorithms to determine the potential alpha energy concentration from radon and thorium progeny in a given volume of air. The detection range is 0.001 to 50 working level. Regarding minimum detectable level, it is 0.001 with 1 hour continuous sampling. I'd like to explain the measurement of an attached and attached fraction. First of all, I'd like to show you the characteristics of an attached fraction. Diffusion coefficient of an attached radon progeny is much larger than that of attached progeny. The diffusion coefficient was first estimated to be 0.054 square centimeter per second, which used to be a single number. Recent investigation had indicated that the unattached progeny is actually an ultra-fine particle or cluster mode, 0.5 to 3 nanometers in diameter, rather than free molecular polonium-218. The higher the aerosol concentration, the lower the unattached radon progeny concentration. The method consists in the sampling of air during a specific period, for example 5 minutes, through an open-faced filter holder that contains a screen and a filter. The filter was used as a backup. A part of the unattached fraction will be collected on the screen, wire screen. The rest of the progeny, namely attached fraction, pass the screen and will be collected on the filter. Two alpha detectors are used simultaneously to measure alpha particles on both the screen and the filter. Look at this. This is wire screen. Unattached radon progeny. Most of unattached progeny are collected on the screen, but attached progeny are collected on the filter. Regarding particle size measurement, the activity size distribution of short-lived radon decay product is a crucial parameter in estimating the radiation dose from inhalation. The amount of location of inhaled activity in the lungs are primarily determined by the particle size. This figure exemplifies the activity size distribution at indoor workplaces. Here is the particle diameter in nanometer, and here is a relative activity. You can find an attached progeny peak. Activity median thermodynamic diameter is 0.09 nanometer. In general, we say an attached progeny. Then we can find the nucleation mode particle, the activity median aerodynamic diameter is 30 nanometers here. Then accumulation mode particle, activity median aerodynamic diameter is 250 nanometers. Coarse mode particles, AMAD is 5,000 nanometers. These three mode particles we call an attached progeny. So I'd like to explain the graded screen array technique, GSA. The measurable range of the technique is 0.5 to 20 nanometers, which is suitable for ultra-fine progeny measurement. There are 4 to 5 stages for detection. You can see this is a sample of the GSA holder. The GSA holder consists of 5 stainless steel wire screens, 30, 145, 200, 400, and 635 mesh. We need a different mesh screens. And a backup filter for attached progeny measurement. After 5 minutes sampling, alpha particles on 5 screens and the filter are simultaneously counted using zinc sulfide scintillation detecting system. Counting data are analyzed by the Thomas method. The other technique, screen diffusion battery method. This is suitable for attached progeny. Measurable range 0.5 to 500 nanometers. It is not suitable for coarse mode particles, more than 1 micron. Screen diffusion battery operates on the basis of penetration probabilities through wire mesh screens as a function of particle size. It is assumed that to a good approximation, the deposition of ultrafine particles on the screen is due only to diffusion. Here is a stack filled with metal wire screen in series like this way. Here's the inlet. Air goes through this way. So we measured alpha activity on the filter here. This slide exemplifies the diffusion battery sampler for continuous measurement. As you see here is a diffusion battery filling with wire screens. Air flows like this way, and penetrated radon progeny are collected on the filter here. On the opposite side, here is a surface, but the silicon surface barrier detector. Here is a low pressure cascade impactor technique for particle size measurement. I can show you the commercial product, namely Moody. Measurable range 40 to 10,000 nanometers. Moody works by using a series of impactor stages with decreasing nozzle sizes. As air is drawn through the device, particles are deposited onto collection plates at each stage based on their aerodynamic diameter. The low pressure in a cascade impactor decreases the drag force on particles, enabling the collection of smaller particle sizes. Micro orifice uniform deposit impactor. Here is the acronym, Moody. I can show the measurement result of simultaneous particle size measurement by GSA and Moody. Here is the particle diameter, and here is a fractional activity. As you see, there is a peak of unattached progeny. Red line represents polonium-218 activity. Blue lines represent a PAEC, potential alpha energy concentrations. And here is an attached progeny. The model diameter is around 200 to 300 nanometers. This distribution was obtained with a measurement in an underground uranium mine in Japan. I will show you another result of simultaneous particle size measurement by Moody. This distribution was obtained with a measurement in a dwelling, Okinawa, Japan. You see, there was no unattached mode, but we could find nucleation mode particles, also accumulation mode particles, and also we found the cosmos mode particles. So I'd like to explain the measurement of surface acceleration rate of radon. This is based on the ISO's international standard. The measurement method for estimating the radon surface acceleration rate is based on the following elements. accumulating radon in a radon-free accumulation container applied to the surface under investigation for non-duration. Sampling a volume of air representative of the air contained in the accumulation container. Measuring the radon activity concentration in this air sample, calculating the surface acceleration rate. Here is a measuring device. This is the accumulation chamber. You see, we have to estimate the effective volume and contact surface and effective surface. The radon activity concentration in the accumulation container increases over time depending on the surface-related acceleration rate, the volume of the accumulation container, and influencing factors such as inadequate air tightness, namely leakage, and back diffusion. The increase of radon activity concentration can be fitted with an exponential function. Here, look at this figure. C, activity concentration in the accumulation container at time t, becquerel per cubic meter. S, effective surface, square meter. V, effective volume, cubic meter. Lambda n, decay constant of radon. Lambda b, time constant of back diffusion. Time v, lambda v, time constant of leakage. Phi, surface acceleration rate. This lambda is effective decay constant. Since the background radon activity concentration in the container is close to zero at the beginning of the accumulation process, the initial slope, the curve, is independent of back diffusion. Here. Assuming that radon loss by leakage is negligible, the accumulation phase can be approximated by a linear increase of radon activity concentration in the accumulation container. Therefore, we can rewrite the equation like this. Radon concentration is proportional to time. Here's the application. This figure shows the radon surface acceleration rate using a continuous measurement method by circulation. This is an accumulation container and high density polyethylene tube. Sampling point is here and continuous radon measurement device with pump. Air circulate like this way. another technique. Radon surface acceleration rate using a continuous measurement method by diffusion. Here is a continuous measurement radon measuring device. Here is the detector and accumulation container. It's a passive technique before this is an active technique. I'd like to introduce our technique that is flow-through acceleration rate measurement system. We use AlphaGuard. This is a pulse type ionization chamber. Open air go into this tube, and here is the accumulation container, and air containing radon go into the AlphaGuard, and the air goes out like this way. Also, we measure the carbon dioxide simultaneously. In this flow method, here is the equation to determine the surface radon acceleration rate. J radon acceleration rate, V sampling flow rate, capital V chamber volume, Q, this is air exchange rate defined as V over capital V. C, radon concentration in chamber after correction. CO, outdoor radon concentration. S, surface area. T, elapsed time from measurement start time. C, CHAM, radon concentration in the accumulation chamber. CBG, background concentration. CF, calibration factor for AlphaGuard. TE, effective time from chamber to AlphaGuard. V1, tube volume. V2, AlphaGuard volume. Here are the critical questions for device selection. When selecting a measurement device, it is essential to think through several factors to ensure optimal performance and alignment with your project needs. What concentration levels do you need to measure? What dynamic changes in concentration are you looking to detect, and over what time frame? What type of analysis are you conducting? Monitoring, screening, or integral measurements? How long will you need to measure without accessing the device? Is the device capable of measuring multiple parameters simultaneously? What are the device's detection limits and range? What are the calibration requirements for the device? here is some information related to international standards. International standards, I would like to introduce international standardization for radon-toron progeny measurements provided by International Standardization Organization, ISO, deal with methodology, International Electrotechnical Commission, IEC, dealing with equipment. You see, as I told you yesterday, there are many international standards related to radon methodology, radon-toron progeny methodology. ISO 11665 Part 1, measurement of radioactivity in the environment, air radon 222, Part 1, origins of radon and its short-lived decay products and associated measurement method. It sets general principles. Part 2, integrated measurement method for determining average potential alpha energy concentration of its short-lived decay products. Part 3, spot measurement method of the potential alpha energy concentration of its short-lived decay products. Part 4, integrated measurement method for determining average activity concentration using passive sampling and delayed analysis. Part 5, continuous measurement methods of the activity concentration. Part 6, spot measurement methods of the activity concentration. Part 7, accumulation method for estimating surface acceleration rate. Part 8, methodologies for initial and additional investigations in buildings. Part 9, test methods for acceleration rate of building materials. Part 11, test method for soil gas with sampling at depths. Part 12, determination of the diffusion coefficient in waterproof materials, membrane one-side activity concentration measurement method. Part 13, determination of the diffusion coefficient in waterproof materials, membrane two-side activity concentration measurement method. Here is another number, 16641. This was project by our research group. This technique deals with radon 220, namely toron. Integrated measurement methods for the determination of the average activity concentration using, of the average activity concentration using passive solid-state nuclear track detectors. So we have another technique for radon in water measurements. 13164, Part 1, General Principles. Part 2, Test Method using Gamma Ray Spectroscopy. Part 3, Test Method using emanometry, this is the gassing technique. Part 4, test method using two-phase liquid scintillation counting. Regarding IEC standard, this organization has one standard on radon equipment, but which consists of 5 parts, recently 6 parts. Part 1, general principles. Part 2, specific requirements for Radon 222 and Radon 220 measuring instruments. Part 3, specific requirements for radon decay product measuring instruments. Part 4, equipment of the production of reference atmospheres containing radon isotopes and their decay products, namely STAR. We call this equipment radon chamber. It's common. Part 5, technical report concerning methods of measurement of radon and its decay product in air. We have part 6, this is under development. It covers passive radon monitor system. This project is initiated by my group.